going to rephrase your question in the framework of particles, but I think I get your question. I think the question is, let's say we have a sphere, and this sphere is settling under gravity with a certain velocity. What you mean by stability, what I understand for that is, does the trajectory remain straight? Okay? So we can ask the same question for a particle. Because in the force balance that I have shown you, this force is steady. Okay? This drag also is steady. This one might be unsteady because you have dV by dt, but it is always along the vertical direction. So from this force balance, it's impossible to predict instability of the trajectory. But if you do experiments, this is something that you can observe. So for example, if you take a particle, a very small particle, it will settle in a vertical straight trajectory. But if you increase the Reynolds number, what will happen? So you see that when the particle is settling, you have a wake here. Okay? You have a wake with two vortices. And depending on the Reynolds number, this wake might be steady. Okay, and this is what I've shown you here. So these vortices, this wake is steady. So it means if you wait, the wake is not, if you wait, the wake is not moving. Okay, it's completely steady. But as you increase the Reynolds number and you do an experiment with a fixed sphere, you will see the wake which is oscillating. And it's called the von Karman instability. You know, you have a wake which is increasing. This is something that you can observe, for example, in river when you have a pile in a river. You see that you have wakes, and these wakes are, you have vortex shading. And because of this vortex shading, let's say you have vortex shading like this, and then you have another vortex here. Okay. And of course, we feel that when we have one vortex which is shed, probably the force, the particle will experience a force which is transverse to the direction of settling. And this is the case. So actually, when you have the Reynolds number which is large enough for vortex shading, then you can observe that the trajectory will be like this. And it's much more complex. It could be like a sinusoid, or it could be like an helix. And it is due to the instability of the wake. So I think your question was, in a car, can we get instability of the trajectory? But even for a simple sphere, it is what we observe. But it is not included in that forces. If you want to include this effect, you have to say that the drag is unsteady. And you have also a lift, which is unsteady. But it's very complex to build these forces related to the vortex shading within a simple framework like this. Okay, so, but this is something which is existing in life. The difficulty is that all these forces has been obtained assuming that the particle is fixed, compared to here where you have a free body. And you have an interplay between the flow, the force which is acting on the particle, and the trajectory, because it's a free moving particle. And you are right, you may have, at certain Reynolds number, an instability of the wake. So I can give you the value actually. The value is at Reynolds 293. At Reynolds 293, the wake is becoming unsteady. And because the wake is becoming unsteady, then the particle is going to move. So I can give you a paper where they looked at this type of instability, and you can have sinusoidal oscillation like this. You can have spherical oscillation, like helicoidal oscillation like that. And there are experiments, they have also some theory, because you have to couple the force with the trajectory equation and with the vortex shading. But it is true. And probably for a car as well. But I'm not a specialist of cars.
Vortex shading effect in the car, moving car.
Yes.
Is
I don't know exactly in a car, but at high Reynolds number, of course, varies.
Because vortex shading is more prominent with a fixed object like a bridge and all this, so that it's, because the vibration is happens, so that it's
no, it's the same. What is important is the slip velocity. So whatever you do an experiment with a fixed object and a flow, or with a car which is moving in a fixed gas, or with a slip velocity, it's the same. The wake and the vortex shading will be exactly the same. The important point is the slip velocity and the Reynolds number. So if you look at probably at the wake behind a car, you have also vortex shading when it's moving. But I guess that this vortex shading is going to drive forces which are transverse, but they are very small. It is, you can see it on a small particle, but if you have a heavy particle, you see the heavy particle, you will have vortex shading, but because the particle is very inertial, the trajectory will remain almost straight. Because you have, you see a balance.
that type of instability for large.
No, you will not see. No, you will not see. You will not see. And this is very, this is what I'm telling you. It's a ratio of the particle inertia to the fluid inertia. For example, this type of instability of trajectories is very prominent for bubbles, because everything is, all the inertia is in the liquid. So as soon as one vortex is shed, the bubble is going to react because it has mass, no mass. Compared to if you take a stone in a gas, you have vortex shading, but actually the stone doesn't care. It will move like a straight bullet. Okay, so it's all about the ratio of inertia of the liquid and the gas and the particle.
Any correlation for wake length? Wake length?
Yeah,
or its usefulness.
Yeah. You can find, you can find correlation for the wake length for particles. There are many. For squares, also you can find correlations of the wake length, and it has an effect on the drag. I cannot tell you that there is a direct link if there's a formula, but there is an effect of the length of the wake with the force, because it will modify the pressure field, and then the pressure is going to modify the drag. So I'm sure there is a correlation. I don't know, there is a relation. I don't know if there's a correlation, but there is a relation between the length of the wake, and you can find in papers what will be the evolution of the wake length behind the sphere or behind the cube as a function of the Reynolds number. There's many papers about that there. Yes?
We have seen that Reynolds number is a function of coefficient of viscosity, diameter, the critical velocity. Then what is the meaning of setting a range of Reynolds number?
What do you mean setting a range?
Means we are saying that 800 to 1000.
Yes.
But it depends on many factors. Then if we take 800, then it may be coefficient viscosity something less and critical velocity something more, and so many probability and permutation combination can be made.
Exactly.
And what is the meaning of setting range? That we are telling that coefficient of
Yeah, but this is the use of the Reynolds number. So I think your question is, if I change the size, if I change the viscosity, will it change the range of validity? Okay, so it's 0.1, 800, 10 to the 5. But actually, everything is embedded into the Reynolds number. Here, I don't have to specify if I'm making experiments in a liquid, in a gas. I don't have to specify if the size is 1 centimeter, if the velocity is 1 meter. Everything is built inside the Reynolds number. And this is the beauty of dimensionless numbers. This is only a function of your shape. If you take a sphere, if you take a sphere, this plot is universal. Whatever the size of your sphere, whatever the velocity of the flow, whatever the viscosity of the fluid, it could be a gas or a liquid, this map, this curve will be exactly the same. Because CD is dimensionless and Reynolds is dimensionless. If you change the shape, so now if you tell me, will it be the same values for a cube, for an ellipsoid, for a complex shape? Yes, of course, it will change the range of validity. It will change probably the correlations, of course. But if you take a sphere, you don't care about the real radius, the real viscosity, the real velocity. The only point, the only quantity which is important is that Reynolds number, which is a combination of all the three effects. Okay, so the range of validity will be always the same if you have a sphere. Whatever, if it's a solid particle in a gas, a spherical drop in a liquid, a particle in a gas, it will be exactly the same. The range of validity is not related to the physical quantities, the physical properties of your system. It is all built into the Reynolds number. Okay, was it your question? Yeah, so this is the beauty of dimensionless analysis, is that you have a physical problem and you are going to extract from this physical problem only one dimensionless number, which is the Reynolds number.
I've got a question.
Yeah.
I missed your lecture in between because of some other administrative work. So suppose if a particle is porous, then what happens? So even say actually the settling velocity, so your free settling velocity, then what corrections do we have to introduce?
I have no precise idea about that. They will be different for sure. But I know that some people work on that. So I know I have some references in head, but I don't know exactly. I
know, because our mind samples, many times, specifically with dealing with your coal or maybe particles, many times they are porous.
Yeah.
And we have no idea about whether they are continuous pore or they are open pore, interconnected pores or open pores. We don't know.
Yeah.
So its velocity will be changing based on how much of fluid is getting into that particle and all this.
I don't think so. I don't think so. I don't think so, because to generate a flow within a porous media, you need a pressure drop, and the pressure drop will be just related to the difference due to based on the settling velocity. And I'm not expecting that there is a difference. No, but of course there will be an effect of the porosity on the mass of the particle and on the effective size of the particle.
Thing is also that is this assumption here is that your surface of your particle will be smooth.
Yes.
But if they are basically they are not smooth. Okay.
And they are not.
If I assume that they are spherical.
But they are not. But they are not. They are.
Then what correction?
What I would say, I think the first in real applications, the first assumption which is incorrect is the shape, and it is there. It is.
But what I am saying that is, if I take even say suppose your spherical balls are made of different materials, so I am having different roughness factor. So is there any correction for this?
You can find, for example, you can find if you look at this, that will probably change here the value when you reach turbulence. It will probably change a bit the factor. I cannot, for sure, for example, when you look at the drag in a pipe, you know that there is a...
Even for the Stokesian range particles, say suppose if I am having a magnetite, I am having
sure.
quartz.
But what I would say, I'm sure we can find people who looked at that. I cannot give you any precise reference. I'm sure that there is a difference, but I would say that the main difference is coming from the shape instead of the roughness.
That is there.
Instead of the roughness. It's much more... The effect is much more drastic than the roughness. The roughness is, I don't think you will see a strong modification in that regime for Stokes.
And then say suppose even in the Stokesian region, suppose all my particles are in Stokesian region, but they are all in free settling condition. Okay, they are not hindered. So if I have say suppose 2 micron particle and 20 micron particle, both are Stokesian. So will it not be the movement of my 2 micron particle will be some kind of affected by?
No, you have to account for it. No, you have to account for that.
To account for that because I don't know the distance between that.
Yeah.
So how do I account that?
So you have to evaluate what is the mean, the average concentration of your system, and then you can use the hindrance coefficient.
No, what I'm saying that the concentration may be less than 0.1%.
Okay.
But then also at that size range, I'll be having say very few particles. I may be having 100 or 20. Say actually your 200 particles. So when I want to account that is when a relatively coarser particle going down. So how the local disturbances are there and whether it is affecting the relatively finer particles or not. Heater setting I'm not talking. Even
Sure.
setting
Okay, so let's say you have only a single sphere which is settling in a suspension, for example.
Maybe.
So this is something that if you have really a scale separation, so I mean if your test particle is much larger than your fine particles, then you can assume that this is an equivalent medium with an equivalent density, which will be an average between the liquid and the particle density. And you can also evaluate a mixture viscosity for your medium of small particles. And with that, I think you can have a good estimate of the settling of your test particle. The problem is coming when I say length separation, I mean a scale ratio like the test particle is, let's say, 10, 50 times larger than the fine ones. If you are in that range, then you can assume that this suspension is an equivalent medium with mixing density, mixture density and mixture viscosity, and that should be okay.
That is when you are taking the say average value of that. But say I can have n number of conditions that 2 particles may be going in a larger volume, but they are very close, they are very side by side, and then when they are basically say apart,
Yeah.
the ROE distances. So your settling velocity will remain same in both the cases?
No, how not.
So how do I know that why the 2 particles are there and all this, because I don't know that.
I can give you the answer if you give me the configuration, because I cannot answer.
Arbitrarily.
Yeah, because if you tell me what is the settling velocity of 2 particles side by side like this with a certain distance, I can give you the answer. If you tell me that the particles are like this, I can give you the answer. If you tell me that you don't know, I don't know either.
What I'm saying, is there any stochastic approach to identify that? That is, if I am having, say, your 10 particles of different and size, but they are all Stokesian, and I have a volume like this, that is the dimension of this. So what is the probability of this, that this particle will be affected by this or this particle will be affected? So you cannot solve it by fluid mechanics, but you have to bring some stochastics. So is there any approach on that?
Yeah. There's a paper by, I think it's by Bachelor, where they look at the settling of particles in the.
Please send me a copy of
Yeah.
that.
So it's a paper. So it's Bachelor.
Actually, sir, recently one paper published in sedimentation hydraulics. They have approached this like particles when moving, they are interacting, then goes into different direction, again try to settle. So concentration bed profile they have measured.
Oh no, that is for hindered setting.
Yeah.
I'm not getting into hindered
No, at
setting.
a very low concentration profile.
Oh,
Even that is also happened.
No, but how do you know that when it will hit or not?
Because they have mathematically proved it.
No, that may be an idealistic case. I'm talking about a realistic case when I.
Yeah, but if you go to a statistical approach, you will get at the end a hindrance coefficient. Because there's 2 ways to look at that. You can say, okay, I want to look at the trajectory of 2 free particles, and then your problem is well defined. You know the distance, and then you get the solution for that problem. If you tell me I want to have a statistical approach of that, what you will get is the mean settling velocity as a function of the concentration, and then you will get the hindrance coefficient.
Now, for another a question, it is for general understanding also, that is for irregular shape, we always talk about orientation problem. Okay?
Yeah.
Now, how frequently that orientation is changing while it is moving? So, can we model that also? Is there any model?
Okay, in Stokes flow, it's quite simple. The point is quite simple, actually. In Stokes flow, the problem is in Stokes flow you have answers, but probably most of the problems are outside. So, but in Stokes flow, for example, if you have an ellipse, let's say that, so you have the sphere, which is very simple, and the next one is the ellipsoid, okay, because you just have to increase one length scale, and then you have a prolate.
That is for regular geometry, but suppose it is irregular geometry. Then how do I know that what is the hydraulic diameter actually basically, and then what is the rate of change of that?
Yeah, you have to evaluate mean quantities, like this is what I shown here. So,
Okay.
so you can find, for example, papers where they try to correlate not here, but here, the fractal dimension or the radius of gyration with the drag force. So you have.
No, and then if I want to do any experiment for that to measure. So
this is based on experiments.
Experiment.
They did. So what they did in that paper is they took a 3D printing system, and then they generate an aggregate that they know exactly what is the fractal dimension as a collection of spheres, and they dropped that in a liquid, and they looked at the settling velocity, and they did the similar theoretical analysis based on Stokes equation, and they tried to correlate the evolution of the drag. I can show you. I have some slides about that was not.
Yeah, these are all PhD topics actually.
Yeah, exactly. So. Yes, that one. So this is, for example, what you say. So you have a collection of particles, which is going to generate an aggregate, and from this aggregate, you are going to evaluate some mean quantities, like the porosity, the radius of gyration, and so on. And based on that, so they did different shapes, which some aggregate are very loose, some of them are very dense than this one, and then they looked at the settling velocity here. So they looked at the settling velocity as a function of this equivalent radius, and they obtained correlation between the drag and the porosity or the radius of gyration. So there are papers, and they did both experiments, numerical simulation, and some theory. So in that case, if we come back to your question about the porosity, in that case, the effective porosity of the system is important, because if you have a loose aggregate, you will have flow inside the pores. But for, let's say, a cold particle where you have micro pores,
Yeah.
I'm not expecting any effect, because the pressure drop will not be strong enough.
No, it has got huge industrial application in our case. That is what is basically involved in population.
Yeah, of course.
But here you already know, because it's a man-made one first, and there I want a in situ flock to be, say actually the grown, and there I may have many flocks which may have different shapes.
Yes.
And they are also changing depending upon the surface phenomenon.
Yeah, and they can break apart, and they can also. Yeah.
Because when they are settling, even then also either they are breaking or they are basically getting agglomerated. So in that case, how do I deal with this type of situations? Can
So
you
you are
on that? Because that will be used.
Of course, but this is the problem between academics and industrial application. If you tell me, can you give me the drag coefficient of that flock, I will be able to give you the answer. If you don't tell me what is the size of the flock, if it's evolving in time, I will tell you, okay, you just have to do experiments and measure. The problem is, how do we relate academic situation where we control the size, the shape, the fluid evolution with real applications where everything is completely unknown.
My question is basically academic. What I'm saying that is, for that you need to know some kind of your stochastic thing also, no?
Yeah, but at the end, what you will get, you will get.
Bring stochastic.
Yeah, you will at the end you will get a correlation at the end. This is the only way to handle a system where you don't know the properties. So you have to say, okay, I'm able to give you the drag coefficient as a function, let's say, of the fractal dimension. In your system, you know that the fractal dimension is varying from 1 to 2.7, and then you will get a correlation. Yeah, you take the average as in, and then if you need more than the average, you will look at the fluctuations, and then your statistical model is going to give you more insight into the moments of your system. But at some point, when the problem is complex, the answer is only based on statistics. So you cannot derive a simple thing. So.
The Brownian motion we are not considering, right?
Exactly.
The particles are very small.
Yeah, exactly. So yeah. So the question is about the Brownian motion. So I don't know if I don't have the slides here. No, I don't have the slides here. But there's something which is very classic. It's called the Cunningham factor. So Cunningham factor is a correction to the drag. Depending on the Knudsen number. So this is existing. So I have some slides somewhere in my computer, but this is something classic. So for example, if you look at the settling of aerosols, like Brownian small particles in air, so you will, they will collide with the surrounding gas particles. This is called the Cunningham factor, and it's actually what you take is the drag coefficient, and you multiply by something which is depending on the Knudsen number, which is a measure of the size of your particles compared to the thermal agitation of the particles.
This is related to mean free path?
Yes, exactly. So the Knudsen number is the ratio between the mean free path in the surrounding fluid, so usually in a gas, this is where it is important, and the size of the particle. So it will tell you if your test particle, what is the size ratio with your Brownian particles, the elementary fluid particles, and then you will have a Brownian motion, and this Brownian motion is going to affect the settling velocity, and it is all included into this Cunningham factor. So this is very classic for aerosol. I'm not telling you that it is correct, but it is classic.
Any other question? Otherwise, we'll break.
Yes.
Regarding this shape factor, one recent article has been published in Power Technology.
Yeah, there's many, shape factor, you can find tons of papers, and they, even for a simple, so I probably have it on my laptop, but even for an ellipsoid, you will see that. So okay, so this is. So if you want to include the effect of shape, so you see that the drag coefficient is a function of the Reynolds number. So this is what I told you for the sphere. So now you are going to include something which is a parameter of your shape. So it could be the sphericity, the aspect ratio, or something. And then very simply, so this is the settling of different shapes. And very soon you will get this type of equations. Okay, so where you get the drag coefficient as a function of the aspect ratio and so on. So at the end, the problem is that you need to know on that sphere, on that ellipsoid, which is not a sphere, what is the drag coefficient when it is moving like this, when it is moving like that, when it is rotating, what are the torques. So this is still under research. So you see drag coefficient, lift coefficient, torque, and all these equations, you can find many papers about that. Basically, it's all related with numerical analysis because it's very difficult to do experiments when the particle is tumbling and so on. But
Fluid flow direction in this picture, what is the direction of fluid flow?
This one? Here, like this. There is a wake. And what they did is to parameterize the drag with the inclination of the particle compared to the flow. So you see here the cosinus, the angle phi is the angle between the flow, which is like this, and the orientation of the ellipsoid. But of course, all these details, you cannot use it in practical applications because everything is going to move inside. So you have to take out all this information and make something simpler to model a real application. But this is something which is under research, so you can find many papers where they try to look into details at the effect of orientation on all the different forces. Because here they did for the drag. You have to do the same for the lift. You have also to do the same for the added mass effect. You have also to do with some other forces that I'm going to present. So it's still under research.